And welcome, ladies and gentlemen, to our lesson for the day, Graphing Rational Functions. It's time we get into it. Our goal today is twofold. First, identify key properties of rational functions. Secondly, then, to take those key properties and allow them to help us graph them. Now, some vocabulary to keep in mind, please. Remember all the things that we have discussed in the past. Solution is a number or numbers that makes a statement true. All the x and y values, for instance, that would apply to this purple problem. We did have problems like this where we have been able to see if this disappeared, we would have a horizontal asymptote at -3. And then examining the domain, the range, thinking about all the x values that would work here. If you started putting in some values, actually, if this simply said the parent function of 2 to the x and x was 0, then we would have our initial point here, right? But noticing we have a -1, it's going to shift us 1 to the right. 3 down, it's going to shift us 3 down. So I'm going to drag this point. I'm going to shift 1 to the right, 3 down. And really, that's the only point that I would need from here on. I see that anytime we multiply by 2, our multiplier is increasing. So we're going to have a function that goes like this. Domain, all the possible x values that would work. In this case, you can have any negative, any positive, any x value at all. I just underlined the range, didn't I? The range is a bit interesting, though, because the range, it cannot even touch -3, but then it's going to go on to infinity. So for our range, we would say not including -3, but then all the way to positive infinity. If you did try to put in -3, well, a y value of -3, it would not work. Those words, we're going to use words like undefined. But that leads us to other questions like, what is this thing called a hole? And is there a way to have a vertical asymptote that we cannot touch? That's where we're heading. If you want to write extra notes in addition to the paper that you got, please feel free to do so. But video is going to be a bit rushed today, folks, just so it's not an hour long. So anytime you need to pause, rewind, go back, think it through, and come on back when you're ready. Now, to review what we talked about on Friday, we had a couple of graphs that we used the Desmos calculator to check into, and we did in fact notice there were these really cool things that we have not seen on a graph yet. There are these vertical asymptotes, to the point where the values x and y that are solutions would get closer and closer and closer to those asymptotes, but would never quite touch. Now think about what this means. This literally means that x cannot be equal to 0. I guess I could have put or equal to, but I also wanted to show you what the equation for the line would be. In this case, we have a value of x equals 3. And think about what would happen if you'd put in 3. We'd end up with something that is undefined. That's, ladies and gents, where we're heading with vertical asymptotes. So two things that we saw new on Friday, vertical asymptotes and multiple curves. Whereas before, if you recall, there was only one purple curve. Now there's going to be multiple curves. And we even had a problem down below that looked even funkier. All right, so pause your video if you want, read on through these notes, circle, underline. I'm going to come back and we're going to focus on step-by-step process. The very first step that you do in order to graph is to factor. You got to factor because in so doing, you will then use the factors to identify any x values that would make the function undefined. In other words, you're looking in the denominator. From there, you should be able to identify what the domain is going to be. In addition, the factoring will show you holes. That's going to be things both in the numerator and denominator that will cancel out. Besides holes, you're going to then start seeing asymptotes. Now, the vertical asymptote, that's the big deal. That's if it's still on the bottom, if it does not get canceled out, if it's unable to be divided by because it would make it divided by 0, that's going to become a vertical asymptote. Horizontal asymptotes can be a lot trickier. For the horizontal asymptote, you actually have to look at the degree of the polynomial. Now, most often we're looking if the bottom degree is higher, you're going to have a horizontal asymptote at y equals 0. That's very common. If the degree is the same, then you have to look at the coefficients, and it's going to be the ratio of those coefficients. We'll get to examples of these, folks. If the top is larger, then there are none. Well, that's only partially true. There are actually some things called slant asymptotes that'll come later in pre-calc, but you don't have to worry about that. For this year, we're going to focus on vertical asymptotes and horizontal asymptotes. If you want, you can go watch a video, look up slant asymptotes, and you'll have some good stuff. You'll see a lot of all this stuff in addition to some extra slant stuff. Now, we will go back to zeros, which lead to our y-intercepts. Remember that the zeros are any x value that would make the y value equal to 0. And you really only have to worry about, after you cancel things, focus on that numerator. Again, we're going to write zeros as x equals, let me write that into my notes. Oops, probably not the best to use that. We're going to write the zeros as x equals 3, x equals 4. But then when we go to the x-intercepts, actually write it as an ordered pair 4, 0. In addition to x-intercepts, we are going to also look for y-intercepts, substitute in the 0. Again, y-intercepts should be written as ordered pairs. And last but not least, if you need any additional points to see where the curves go, we're not really going to make a full table. We'll actually only pick 1 or 2 or 3 values to the left and to the right of the vertical asymptotes. Remember, don't forget your holes. We'll show you what those look like on the graph momentarily. Again, you can pause, mark up your notes if you want, but let's go ahead into an example. Now, for this first example, I'm really just going to focus on the key information. We'll come back to the graphs later. I'll even go into 2-page mode so you can stare at this. Now, we notice, oh, it doesn't let me use disappearing ink in 2-page mode, I forgot. We notice factoring is pretty much already done. I mean, I don't have to write that check mark, but there is no factoring to be done. But I am going to look for any values of x that are no-nos. And in this case, if x were equal to 1, we'd have a severe issue. Let me just show you this. Y equals 2 over 1 minus 1. Y equals 2 over 0, which cannot be done. That is undefined. That is not real. So that will tell me that my domain is not going to include 1. So if I started at all the negative x values all the way to negative infinity, it's going to go to 1. And then after that, it's going to go from 1 to positive infinity. Notice that 1 is not included. We're not using brackets. One final note, we're going to put a little u in here, and that u literally means the union of these two parameters, the union or putting together the two parts. I don't really need you to understand what that union means for now. Just note that we're going to have two pieces of this, and I'll even show you later on when we graph it where that domain comes from. Are there any holes, ladies and gents? Well, I don't happen to see any holes. There was nothing that would both cancel out on the top and the bottom. So for holes, we're going to write not applicable, NA. Vertical asymptotes, those are the x values that cannot be used. We already said that x cannot be 1. So actually, I'm going to write it as a line, x equals 1. And I'll show you later what that looks like on the graph. For the horizontal asymptotes, that's when we have to look at this. This could be one of the trickier parts. Because we have an x to the first in the denominator and an x to the 0 in the numerator, we have one of those instances where the bottom degree is higher. Therefore, sooner or later, we're going to see our curves approach that. But let me just delete that off the graph for now, because I just want to focus on finding the information. All right, x-intercepts. We're looking for any x value that would make the y equal 0. So if I wrote this, and I substituted in 0 for y, notice please, if you multiply by the denominator, that would cancel out. But we end up with 0 times anything is 0 and 2, and that's just Not going to happen. So in other words, there are no x-intercepts here. We're going to write not applicable, x-intercepts, not applicable for the zeros and the x-intercepts, which kind of makes sense because remember, we said there's going to be an asymptote at 0. Last but not least, let's look for our y-intercepts. In other words, what would the y value be when x equals 0? So if we put in y equals 2 over, now substitute in 0 for the x value, it ends up being 2 over negative 1, which is negative 2. So when x is 0, y is negative 2. Now, folks, some of you are itching to go into the graph, but I'm actually going to leave it at that, and I'm going to go on to the next point. We're just going to find these original, find the original information, the key properties. Okay, we immediately notice for problem B, this is not factored, at least not yet. Now that's why the factoring piece is so important for you guys. In this case, the denominator is going to be a little simpler, and that's going to be x plus 1 times x plus 3. Numerator, little tougher. If you need, go off to the side, do your box method, do your magic x, or do the Mrs. Willard way. One way or the other, you're going to get 3x minus 2 multiplied by another factor of x plus 3. Now, you might immediately notice something, and you might be itching to get there. But notice, please, that the x plus 3's will cancel out. That, ladies and gents, is what leads us to a whole. Now think about it. X cannot equal negative 3. If x was negative 3, we'd have 0 times something in the denominator, and 0 times anything is 0, and you cannot divide by 0. So, x of negative 3 is not a point that we can use. I'm going to go ahead and write that. Meanwhile, I noticed another x value that cannot be used. If we have x of negative 1, we're in trouble. That might lead you to a vertical asymptote. Notice negative 3 is not a vertical asymptote because they would cancel. It's still discluded, it's still excluded. So that's what we're going to call a hole, and we'll show you later on what that looks like in the graph. But negative 1, that's going to be an asymptote. Now, how do we turn both of those into the domain? Well, if we were to start at negative infinity, the first stumbling block we'd get to is negative 3. Then there's going to be an interval from negative 3 to negative 1 that's going to be okay, but then we're going to get into another stumbling block at negative 1. Finally, after we'd crossed that negative 1 obstacle, then we can go all the way to infinity. And don't forget to put the union symbol, the basic U, in between all of them. Again, if you ever need to pause, go back. Please do. For the horizontal asymptotes, folks, we basically have to say, okay, the degrees of both numerator and denominator are the same. If we look at the ratio of that, 3 to 1 is equal to 3. So we're now going to have a line y equals positive 3. That's going to be a horizontal asymptote similar to what we've seen in the past. Zeros, we're looking for x values that would make the whole function equal 0. So if I set y equal to this, now look, I'm going to show you this the long way this time. And then I'm going to just focus you on the numerator from here on out. 3x minus 2, x plus 3, x plus 3, x plus 1. Remember, please, to simplify our lives, cancel those out. Multiply both sides of the equation by x plus 1. In so doing, that cancels out the denominator, and all that's left is that numerator. Well, excuse me, all that's left is the piece of the numerator that does not cancel. And of course, 0 times anything is going to be 0. So really, from here on out, all you have to look at is the part of the numerator that does not cancel out. What would the x value have to be in order to make this equal to 0? Well, if we add 2 to both sides, divide both sides by 3, we find a fraction. For you decimal lovers out there, you're welcome to do that. Now I'm kind of running out of space. I'll try to squeeze this in. I might have to erase. So x-intercept, when x is 2/3, y is 0. There was no other possibility. Again, you almost wanted to say -3 was a possibility. But remember, x cannot equal -3. That would have made the denominator 0, and that would have totally messed us up. All right, so let's try to find the y-intercept. So when x is 0, what would y be? So I'm going to go ahead, I'm going to go back to this, and I'm going to substitute 0 in for everything. Let me put a little 0 here, a little 0 here, 0 here, 0 here. But again, you really don't have to worry about this right side. In the numerator, we'd have 3. In the denominator, we'd have 3, and those would cancel out. So I'm not really going to worry about that. That's going to leave me with 3 times 0, which is 0, minus 2, which is -2, 0 plus 1, which is 1, and -2 divided by 1 is -2. So we've now found a y-intercept at the point 0, -2. Don't really know what's going on with my color scheme, folks, but that's okay. Again, pause on the graph. Let's just go on to the next example, and I want you to see if you can pause, try to factor this, come on back when you're ready. If you were to go in a different order, you might have noticed immediately that the degrees are the same. So we'll have a horizontal asymptote at 1 to 1, or 1. But I'm not encouraging you to go in different order. It just might be there if your brain is there. Meanwhile, in factoring part C, you're going to get in the numerator x minus 1 multiplied by x plus 2. In the denominator, x minus 3 multiplied by x plus 2. And immediately you'll notice when it comes to the domain that x cannot equal 3 and x cannot equal -2. But which of those are asymptotes and which of those are wholes? Well, the -2 is going to be what's canceling out. So our first whole is going to be at -2. Our vertical asymptote is going to remain there. We better not ever choose +3. Which means we can now use this to form our domain. From -∞, first stumbling block we get to is -2. If we cross over that boundary line, -2 will take us all the way to 3, but then we get stuck again. From 3 would go to +∞, and I'm going to go ahead and delete those things. And we will show you once again when we get to the graph what that looks like. All right, zeros. Are there any zeros? Is there any way to make this function equal to 0? Now, again, I showed you last time, over here on the previous example, well, you don't have to worry about the quantities that cross off. And you don't even have to worry about the denominator, because in multiplying anything times 0, we'll still get 0. So I'm really only going to focus on 0 is equal to x minus 1. In so doing, I found a 0. If you substitute in 1, the y value will be 0. If you don't believe me, you can do it. You can try it. You can substitute it in. You'll end up with 1 squared, which is 1, plus 1, which is 2, and 2 minus 2 is 0. And no matter what you got down below, 1 squared is 1, 1 minus 1 is 0, 0 minus 6 is -6. You can see that, yes, in fact, 0 divided by -6 is going to give us an output of 0. And let's wrap up with, oh, I shouldn't erase that. Let me put that back. Let's wrap up with a y-intercept. So what would y be when x equals 0? Again, you don't have to worry about the parts that cancel out. So I'm only going to substitute 0 in for the two parts that remain, 0 minus 1 and 0 minus 3. We end up with -1 over -3, which is a positive 1/3. So when x is 0, y equals 1/3. One more, folks, and I would encourage you to pause the video, work it all out, come back and check your answers, and I'll do this one a little faster because of that. Come on back when you're ready. Factoring, we'll get the product of x minus 2 and another factor x minus 1 down below, x plus 1, x minus 1. Quickly we see here, we better not let x equal to -1. nor should we let x equal to positive 1. Because the positive 1 are the factors that cancel out, that's going to be a whole. We're going to learn what that looks like on the graph in a moment. Vertical asymptote, x equals negative 1. Domain, negative infinity to negative 1. Cross that boundary, negative 1 to positive 1. Cross that boundary, positive 1 to infinity. And I forgot on the last example to put the union symbol in between, so that we say we're going to put all those pieces together. All three of the pieces are what are going to describe the domain. Horizontal asymptote, same degree, both the numerator and denominator have a degree of 2, so 1 to 1 reduces to 1. We have a horizontal asymptote at 1. To find our zeros, we're looking for a y value of 0. We don't have to worry about the denominator. We don't have to worry about the parts that cancel out. The only thing that is going to help us here is x minus 2. And if you forget that, that's okay. You can go back, you can do the whole thing, you can solve it like we did the long way before. In this case, if x equals 2, y would equal 0. Then let's look at the y-intercept for the y value. We don't have to worry about the parts that cross off. We're only going to worry about the minus 2 and the plus 1. If we input 0, our output would be negative 2. So when x is 0, y is negative 2. All right, folks, you got the bulk of the work. From here on out, we just have to put these into graph form. So I'm actually going to go back to problem A, and we're going to graph what we have. Will it let me scroll down? That could be a problem. Might have to do this one at a time. Oh, it did let me scroll down. Good. All right, so the first thing that I tend to do is I put in my asymptotes. In this particular case, let's get some nice. I noticed a horizontal asymptote at 0. That's kind of what we're used to. But in this case, we finally have a vertical asymptote that we have not really seen before. And that vertical asymptote is going to be right at that positive 1. Now, there were no zeros. There were no x-intercepts. But there is a y-intercept. So let me go to my pen and simply mark the point 0, negative 2. Now from here you can use logic, but we're basically going to test points. And I might need to go to one-page mode here so I can get the whole page. We're basically going to test points. I know your notes are kind of small, so just squeeze them in where you can. We're going to test points to the left and to the right of those. But logic says this guy is probably going to go right there. But let's go ahead and test that just to make sure. So I'm going to test negative 2. And I want to find out what would the y value be when we input negative 2. So y equals 2 over negative 2 inputted minus 1, 2 over negative 3. So when x is negative 2, y is negative 2/3, and that just verifies. Folks, that's really all we need. Some of you might have, I got to make sure that doesn't look like it touches the blue, if you understand what I'm saying there. Because for the asymptote, that's literally what it means. It'll get closer and closer, but x cannot equal 1. If you put in 1, boom, it's going to blow up the whole thing. It's going to make something that's undefined, so it won't work. But you could put in 0.9999998779999. Those inputs are going to be okay. Hey, let's go ahead to the right. Always test a point on the right. So let's go with 3. When we input 3, what would our output be? So we put in y equals 2 over 3 minus 1. When x is 3, y equals 1, which is going to tell us also, you can put in more values if you want, but no calculator is going to be allowed on the quiz. You might as well pick nice values. Now we can see two curves, two separated curves. One curve on one side, one curve on the other. Neither curve will ever touch that vertical asymptote. They won't touch the horizontal, although I wonder, I'm going to plant a little seed. Is it possible for a curve to ever cross the red horizontal asymptote? I'm going to plant that seed. I'm going to let you figure that out later. All right, let's go back to our lines. First thing that I see is negative 1 for the x. So I'm going to plot a vertical asymptote at x equals -1. Now I'm going to notice that there is a horizontal asymptote at y equals 3. And interesting here, I have this whole thing now. I'm going to put a little star next to that, and we're going to come back to that later. Meanwhile, we have a couple points to plot. When x is 2/3, y equals 0. When x is 0, y equals -2. And folks, honestly, that's enough for us to see where that curve is going to be in the lower right-hand quadrant. It's going to approach that blue asymptote but not touch it. It's going to approach the red asymptote but not touch it. Now what we got to do though is we got to say if x was -3, is the point going to be down below or is the point going to be up above? We don't know yet. That's what we're going to find out. So let's go ahead and input -3 and figure out what comes out of it. Y equals, now remember, you don't have to worry about the parts that cancel. So in the numerator, we have 3 sets of -3 minus 2. Denominator, we have -3 plus 1. That would simplify to -2 down below, -11. And we end up with 11 halves, 5 1/2. But you know what? That's enough information that we need. If we input -3, our output would be 5 1/2. -3, 5 1/2. And that's enough for us to figure out it's going to go over here. Now, this was not the best of points to pick. I really should have tried -2, and I want to do that right now, and I'll show you why later. Or let's go to -4. Why not? So if we input -4, y is going to be -3 times -4, subtracting 2. Down below, we have -4 plus 1. That simplifies -3. This simplifies. I don't know why I said that was -3. It was a +3. -12 minus 2 is -14. We end up with 14/3, which is going to be the same as 3 is going to be 4 is going to be 12, 4 2/3. So that does verify. Again, you notice my graph is not perfect, right? Now, why did I decide that -3 wasn't a good point? Ladies and gents, we can't literally have a point at -3. I know we actually came up with something, but if you went back to your factored amount or to the original and you input -3 in for x, you input -3, you're going to get a big old 0. It's going to blow it up. Folks, we need a hole to point out that it would blow up. So I'm going to go to -3, I'm going to follow that up, and I'm going to erase it. And to show that it can be to the left of -3, it can be to the right of -3, but it can't be 3. Boom. There, ladies and gents, is what a hole looks like. It's basically an empty dot. It's an open circle stating that, look, x can be anything from -3 to infinity. It can be from -3 to -1. It can be from -1 to infinity. But it cannot be -3 because that would blow it up. It cannot be -1 because that would create an undefined quantity. I think you just found out one of the most important parts of today. Not only are we getting into vertical asymptotes, but we're now getting into holes. So keep your eye on holes in the future, what they look like, where they're going to be. And I'll try to do a better job with teaching. Let's go on to example C, and we're going to graph everything we got. Firstly, we found that there was a vertical asymptote at x equals 3, so I'm going to go ahead and draw that vertical line. There was a horizontal asymptote at y equals 1, so I'm going to go ahead and draw that horizontal line. Are there any points that we know of? Well, when x is 1, y equals 0. When x is 0, y equals 1/3. And I do believe, folks, that's enough to tell us this part of the function. From +3 to -infinity, we're going to have a curve, an xy series of values, infinitely many solutions, to be honest, but it's going to be to the left and down below. Now, what's going on with, let's try 4. Let's figure out, where is it going to be? Is it going to be down here? Is it going to be up here? So I'm going to input 4 in, and when we do that, I'm going to use the factored expression. It'll be a little quicker. 4 minus 1, 4 minus 3. That would simplify to 3. So when x is 4, y is 3, that's probably enough. If you want to do an extra point or two, you're welcome to it. I would suggest 5, 6. You can do 3.5, but that's going to be kind of hard to do without a calculator. In this case, we know that this curvy part of the function is going to be in the top right-hand quadrant. But your alarm bell should be going off. Hold on, Mr. Callan, hold on. We said that, sure, 3 is going to be discluded as a domain member of the domain, but so is -2. So what I have to do is I have to go find -2. I have to go up to this with my little eraser, and I have to make sure that I have put a big old hole at -2. That didn't look very great, so let me try that again. The point is, I could use -1.99, I could use -2.0003, but if you put in -2, -2 squared is 4, 4 minus -2 is +6, 6 minus 6 is 0, and it would create an undefined quantity. You cannot do that. So there's another example of something that has both a vertical asymptote and a hole. If you haven't done this yet, you can go ahead and pause, do this graph, come on back when you're ready. Vertical asymptote, -1. Horizontal asymptote, +1. Point values that can be substituted in. X-intercept at 2, y-intercept at -2. Shows us that part of the function, but let's go ahead and test something out. Let's test -4. Going to the function, you must only have to use the stuff that doesn't cancel. Let's go ahead and input -4. We end up with -6 over -3. So when x is -4, y is 2. When x is -4, y is 2, which shows us this part of the function is going to go as such. And last but not least, and maybe one of the most important parts of the lesson, x cannot actually equal 1. So let's find that 1. Let's go ahead and take our eraser and go straight down and say, hey, there's a hole at 1. Now I know our graph isn't perfect. Maybe it's not at, the hole's not at 1, -2/3. We don't know, but it's good enough to show this. Folks, a 7th or 8th grader can make an XY table and draw some curves. And notice that those curves will not touch -1 or not touch y equals +1. But we're trying to test your understanding of graphing rational functions without XY tables, without using the graphing calculator. Speaking of, if you ever get totally jammed up, you can go to that graphing calculator and you can test your points. Or excuse me, you can just graph it out. So for instance, if I come over here and test what we just did, let me find the one that says x squared minus 3x plus 2 over x squared. There she is. Now I even put in this to test are my vertical asymptotes correct? Was my horizontal asymptote correct? And if you really wanted to dig around, you could try to find that hole. It's a little hard to figure out because you're going to have to scroll. They don't show it. Oh, bam. And now it becomes a hollow, empty dot. As soon as you move to the left or to the right, it's not going to be. The reason that doesn't show on the purple is because you could zoom in and zoom in and zoom in and zoom in and zoom in ad infinitum for infinity and beyond. And I think I just lost the x equals 1. The point is you can keep zooming in and they have to keep showing there's purple. The computer literally just can't be programmed. Maybe it can, I don't know. But again, you can find an open dot at y equals 1. All right, folks, that's enough for the video. I might make another video. Go ahead and start the extra practice on the backside. Maybe I'll just show you answers, or maybe I'll make another video. We'll see if we have time to do that. Good luck. Do well.